Hello, it's Stat 135, Lecture 31. Last time we were in Section 12.2 doing ANOVA. We have I treatment groups and JI observations for each of I groups. And assumptions of our model are that our observations Yij are normal, that the variance of all these observations is sigma squared, that the treatment groups are independent and observations in each treatment group are independent. So the F-test is a test statistic that follows the F distribution, which has two parameters, 2 degrees of freedom. So for us, the degrees of freedom are going to be I minus 1, because the numerator is going to be essentially it's going to be a chi-squared with I minus 1 degrees of freedom, so SSB, and the denominator is going to be a chi-squared with the sum of Ji minus 1 degrees of freedom. It's going to be SSW. So SSB and SSW can be calculated as given in these formulas, and we've seen this a few times now. So if we reject the null, we do the shortcut Bonferroni by comparing I confidence intervals, and these confidence intervals have significance alpha over 2I. So it's alpha over 2 because we're doing a two-sided t-test. Generally, if it's a one-sided t-test, then it would just be alpha over I, but generally it's a two-sided t-test. And so we have I of these confidence intervals, and that confidence interval is given by the formula here. So we have the treatment mean plus or minus this cutoff times the sample variance of that treatment group over square root of n. So n here is the number of observations in the ith group. And to find the cutoff, you can use actually a Bonferroni table to find this, and let me show you that. So that's here. So in a Bonferroni table, you need to know the degrees of freedom. So that is n minus 1. N minus 1 is the number of observations in the ith treatment group, and then it's then you need to know the number of tests. You have k, which is for us I, the number of treatment groups. So then what we get here is a threshold, right? And so this can be convenient to use. Oops. So today what we're going to do an F-test in class exercise, then we're going to do the Kruskal-Wallis test, which is a non-parametric test, a Kruskal-Wallis test in R, and then practice by hand. So here is a in-class exercise, lecture 31. We do some data cleaning so that we can easily make QQ plots and box plots for our data, and it looks good to go for an F-test. I'm computing by hand the SSW and the SSB and the F statistic and the p-value of the S statistic, which is really small, so we would reject. I do that by hand because I don't like black boxes, but here is a black box. One-way dot test is a you just enter the treatment and a vector of the group sizes and whether your variances are equal or not, which hopefully they are, then out it spits the p-value. So it gets essentially the same as what we got. So next we do the Kruskal-Wallis test, which is a non-parametric test, it is a generalization of the Mann-Whitney test to two or more treatment groups. Remember, the Mann-Whitney test is a test for unpaired. It's a non-parametric version of an unpaired t-test, right? So here we have the non-parametric version of independent treatment groups. And so Rij is the rank of Yij in the combined sample. So you combine all of your treatment groups and you're just ranking all of the observations. So we also find the mean of the ranks among each group and the total mean. The total mean is just n plus 1 over 2. And we can calculate SSB of the ranks just in the usual way. So this is a measure of the spread of the average rank of groups around the total rank average. And if the null is true, then each treatment group has the same distribution. If the null is true that each treatment has the same distribution, then the SSB should be small because all of the average ranks should be around the same. So as before, SSB over the variance of the ranks is a chi-squared I minus 1 degrees of freedom. The problem is that we don't know what chi-squared of the ranks, sigma squared, the variance of the population variance of the ranks. We don't know what that is, so we approximate it by the sample variance of the ranks, which is 1 over n minus 1 sum I minus n plus 1 over 2. So I here is just all of I goes from 1 to n. That's all of the ranks that we have. And the average rank is n plus 1 over 2. So that is just the sample variance. And some algebra shows that is n times n plus 1 over 12. So our Kruskal-Wallis test statistic is the SSB of the ranks over n plus 1 over 12, which is a chi-squared I minus 1. So you can test whether it's large, and if it's large, then you reject the null. So we have some example in R, and I did it out by hand, so it was a bit of data wrangling to get it in the form I want, but no problem. You can just calculate the p-value directly, or you can just use Kruskal.test and do it very easily. So you end up rejecting the null. So finally, we did a example in by hand here. So here we had 3 treatment groups. Each had n observations. We were given the mean weight for each group and the SD for each group. So we also have the F table and also our Bonferroni table. So to solve this, we calculate the average variance of the 3 groups, and this has 12 degrees of freedom, which is the sum of the ji's minus 1. So that's 4 plus 4 plus 4. And the total mean is just the average of the 3 means given, because all the sample sizes are the same. And so then we get the variance, the sample variance of the group means, and that's 175. And we can calculate the between sample variance, which is 5 times 175, or 875. So this has 2 degrees of freedom. So F is the between sample variance over the within sample variance, which is 2.37, according to the F table, with degrees of freedom 2 and 12. 2 and 12, we get 3.89 is our cutoff. And we got 2.37, so we do not reject the null. But we're going to do a Bonferroni t-test anyway, just to illustrate it. So we have alpha over 2 over 3, so that's 0.00833. So we're going to show that the 98.3% CI, we have three 98.3% CIs, and we're going to calculate them. And so I do that here, and I get the cutoffs for each of the, like T4 alpha over 6. I get that from the Bonferroni table. And you can see these three intervals do not all overlap with one another. So it is possible that the true population mean is the same for all three groups. Great. Have a great weekend, guys, and I'll see you on Monday.